I'm really excited to be here and present to you guys a guide about best practices for Ethereum front-end developers. And this presentation isn't going to be exclusive to the Ethereum network. It's going to be very multi-chain focused to figure out how you can actually build applications which are querying all of these different networks and doing all of these complicated things. So my name is Andrew Schmidt. I'm a DevRel engineer at the Aave companies. I actually just recently transitioned to developer relations. Prior to that, for the last 2.5 years, I've been a full stack engineer at the Aave companies, primarily contributing to the open source Aave interface. So I've gotten to see a lot of the challenges that go with building and maintaining these types of interfaces. And I hope that I can give you guys some knowledge to help you build your own applications. So to start off with, this presentation is going to go through a lot of different concepts and a lot of different tools. So I just created this link tree, which has a lot of the resources which I'm going to be going through. Feel free to just, during the presentation, just check them out. I'm sure that there's probably something you haven't seen before that might help you a little bit in your development journey. And also we'll have this at the end of the presentation too. So what is the motivation behind this? Really, when I was making this presentation, I was trying to decide between building an application from scratch, from the ground up, or doing what I decided to do here, which is actually just give a more broad overview about the best practices. And really the main goal of this presentation is to focus on the experience layer. It's not about building applications, it's about building experiences, both for the users and also for developers, and also to address what's coined in this book called the cold start problem. So the really key concept that I like from this book is the idea of an atomic network. It's that in order for an application or for the front end to really reach, a velocity where people are actually coming in and using it organically and sharing it with other people, you have to have this sort of atomic network, this stable group of users who are fans of your application, who are regular users of it. And I think that particularly for Ethereum front ends, it's quite difficult to overcome this hurdle because there are so many technical expectations. As users, we expect certain things from our dApps, from wallet connections to transactions to speed. And if an application doesn't have all of these things, it's really difficult to gain this atomic network. And specifically with hackathon projects and Web3 startups, you really notice this where they have these phenomenal ideas, but they're really just not able to gain traction because they don't have all of these fundamentals when it comes to these front ends. And so kind of this presentation is meant to give both the technical and kind of the user experience that is really needed to get a baseline application for Ethereum. And so where does every good building project start? It starts with a plan, the architecture. And so really the question that you have to ask when trying to plan out your front end is, how is your front end going to interact with external things? If you think about like a traditional Web 2 stack, you kind of have this large backend, which is performing most of your logic. It's querying APIs, it's housing all of your data, and it's really just creating these simplified endpoints so that your front end can just be this very simple view layer, but all it's doing is displaying data. Whereas in Web 3, you kind of have the roles reversed, where your front end is actually doing a lot of the work. Because as we'll see throughout this presentation, blockchains are not really a substitute for a backend. Essentially, you're limited to only the view methods that the blockchain allows, and then obviously the write transactions. And a lot of times you also kind of need this sidecar where you're having this indexed data where the blockchain itself can't provide what you need, and so you sort of need these services. This is sort of a very general overview of this. Obviously, there are blockchain front ends which use backends and which abstract a lot of this stuff away. But typically, if you look at the largest DeFi applications, they follow this framework where they have a blockchain and then most of their logic exists on the front end. So as you see, like the business logic and the wallet state is all handled in the front end. And so we're kind of going to try to make sense of how you can actually architect your application around this. And so obviously the first place that you have to start is smart contract interactions. If you don't have solid interactions, I really don't think you can have a solid dApp. And the most common ones directly are reading and writing data. And then you have these more indirect things which are not directly communicating with the blockchain, but they are in some way involved. So that could be indexing data, interacting with the user's wallet, like fetching chain ID, like fetching the current network state, and then account abstraction, which we'll briefly cover as well. So just diving into the direct interactions, this follows actually a pretty standard path. I think just about any Web3 application will follow these standard steps. So first, you're going to start with a Web3 library, something which is going to actually handle these blockchain connections. You're going to pass in an RPC. This is your connection to the blockchain. And then based on that RPC connection, you can interact with contracts, and kind of the two steps to do that are passing in an address and then an ABI. And then from there, like once you have these Web3 libraries set up with your contracts, now you sort of have this SDK where you're able to call these read and write methods. And so what does a contract call actually look like? This is sort of getting pretty low level, but I think it's really important to go through. So basically, any time that you are reading or writing to a smart contract, you're going to follow this standard path where you're designating a to address, the address that you're sending the transaction from, and then you have this transaction data. And this transaction data is actually static, and it's very important to understand like what the architecture of this is. So first, you start off with a function selector. This is identifying the function that you're calling. So for example, I pulled this from an Aave contract. I think this is setting a user's E mode, and then the rest of this call data is full of the parameters. And these parameters are actually following a formula. So if I, as a user, call this function, it's going to be the exact same function call, the exact same transaction data as if another address was calling this transaction data. And so why this is kind of important is that, for most users, you're going to interact with these protocols through a user interface, your app.aave.com, app.uniswap.org. For your more advanced users, they might be able to kind of interact with the contracts directly through Etherscan, reading and writing. But really, once you understand the basics of what this transaction data is and how to read and write contract calls, you unlock sort of this third skill, which is being able to build transaction data from an ABI. And I think once you're able to do this, it unlocks the ability to build things, but more importantly, it unlocks the ability to debug things. So in that link tree, I had a couple of resources here that you can see exactly how you can decode and encode this data. And then Tenderly is a tool which we're actually going to do a deeper dive into later in the presentation, which actually really lets you take it to the next level and debug these transactions. So that's kind of the end of the direct section. So when it comes to historical data, one of the things that a lot of newer developers have a hard time grasping is that that even though the blockchain stores the complete history of transactions, at any given point, you're really only able to query the live state without going through some hurdles. So yeah, direct contract calls can only query live state, and the events, which are the historical transactions and also the call data which generated those events, they can be queried through RPCs, but this is a very inefficient process. You will almost never see a blockchain front end querying events directly on the front end, unless it's for a very specific use case. And so most commonly, you're going to access this historical data through things like indexed data sources. Some of the most common ones are the graph, subgraphs, which are defining GraphQL mapping for your contracts, and some alternatives, TrueBlocks, Ref Indexer, which is actually being built by one of the employees of the Aave companies. And then you have this Lens API for the Lens protocol, which sort of aims to abstract basically the entire tech stack. So that's kind of the data side. The other really big thing to understand about contract interactions is signatures. Signatures are something which can really, really boost the user experience of your application if implemented correctly. But a lot of developers sort of overlook them and just really default to the transaction workflow. So what exactly is a signature? Well, it's just a message which is signed by a private key. And what this means in practice is that basically the message signing is local. All that's happening is that your front end is sending a request to the user's wallet. It says, I would like you to sign this piece of data. And if the user signs that piece of data, it's signing it with their private key. And all it's doing is sending a string back to your application. So when you click this sign button inside of MetaMask, nothing is actually happening on the blockchain. All that's happening is that you're generating this signed string. And what's really important after that is what can you actually do with these signed strings? So I'm going to throw a couple numbers at you, but hopefully it's not too overwhelming. EIP 712 is sort of the basis for signing messages. It defines how you're able to send an object to the user's wallet, which breaks down exactly what they're signing. And then EIP 2612, also called permit, standardizes the process of passing data to the user's wallet, which enables them to approve the token. So I think most people know that in order to send an ERC20 token to another address, you first have to approve that token to be sent from one address to the other. Permit is an alternative approach to this. And the way that it works is that your front end is going to send a request to the user's wallet to spend a certain amount of tokens to a certain address with a certain deadline. And then once the user actually signs that message, as I mentioned here, nothing is actually sent to the blockchain. That signature is stored inside of the application, and then it's actually up to the application to decide when is that permit going to get called. And so this is one example within the Aave smart contracts of where a signature is actually used. So the line which is most important is right here. Basically what this line is doing is this above section is basically constructing based off of the parameters that are passed in, the delegator address, the delegatee, the value, and the deadline. It's going to construct a piece of data that says this represents a valid signature. And then it's going to use this function called EC recover. It's going to take also I should mention the V, R, and S parameters that are passed in here. These are actually what is returned by the wallet. So when you send the signature request, the wallet signs it, it's going to send back a string, and you can decompose that string into these V, R, and S parts. So whenever you see V, R, S, you can kind of just mentally think of it as signature. And so when you call this EC recover, it's saying, okay, based off of the parameters that you passed in and the signature you passed in, does that elliptical key mapping map back to the original address? And if it does, it says, okay, this is a valid signature, so we can go ahead and perform whatever action you want to perform. And in this case, within the Aave contracts, this last line here, approved delegation, this is normally something that would require you to submit a transaction to do. But by doing it based off of a signature, the end user does not have to be the one which is submitting this transaction. And one other note about signatures is how they interact with smart contract wallets. So smart contract wallets don't have a private key, which means that they're not able to use this EC recover function. EC recover is an elliptic key mapping from the private key back to the original public key. And so they're not compatible with this. And that means that smart contract wallets are not able to call permit. They're not able to call any function like the one I showed on the previous slide, which is using EC recover. But they do have this thing called EIP 1271. And this allows a smart contract to validate that a signature is valid. So instead of actually signing a message, EIP 1271 takes basically the opposite approach. It says, okay, for a smart contract wallet, what we can do is you can have this function called isValidSignature, where you pass in the actual signature and it's going to return a value. And if the contract is validating that signature is valid, it's going to return what's called a magic value. It's basically equivalent to passing true or false. So the very simplest isValidSignature you could create is just always returning true. But obviously you could create any logic inside of here where you could say, my signature is only valid if, say, it's a multi-signature wallet and 2 of the 3 signers have validated that transaction. It can implement basically any signing logic. And so this sort of leads to the next thing, which is gasless transactions. This is really the whole purpose of why we're trying to get into signatures. And really, gasless transactions are possible to facilitate at 3 different levels. So at the protocol level is sort of what we kind of went through in that slide where I went through the code. Basically, within the Aave contracts, it's defining that if you pass a valid signature, I will let you call this method, even though you might not be the original delegator that is sending it. And then once you have this signature, instead of the user sending the transaction, the transaction can be sent from something called a relayer. This is also sometimes referred to as meta transactions. It's the same concept. And basically, you have services like OpenZeppelin Defender or the Lens Dispatcher, which basically allow you to create these relayer services. And it says, you can submit this transaction on chain, and the gas cost will be paid by this separate entity as opposed to the end user. And the same thing sort of happens at the wallet level. EIP 4337 is, you've probably heard it many times, but it's very, very important to understand the ins and outs. I'm not going to go through it too deep here because it could be an entire presentation, but sort of at a high level, what it does is instead of submitting transactions to a mempool, you're submitting these things called user operations. And user operations are a lot more flexible, and they also allow you to have what's called a paymaster, which is the address which is going to pay the fees for that transaction. 4337 is actually a lot deeper than just gasless transactions. You can do all kinds of different validation. And then sort of along the same lines, you have networks like StartNet, which are actually implementing this abstraction, which is very similar to 4337, but it actually happens at the network level. So the network allows you to basically delegate these transactions to another wallet. And yeah, some resources here to learn about those are in the QR code. And that's kind of like the technical overview. Like if you understand how to write transactions and how signatures work, those are basically the core components of how your dApp is going to interact directly with smart contracts. So now we're going to go into some practices of, how you can actually take these and use them inside of your front end. And so if you have one takeaway, I would say that if you want to build a front end, which is actually going to be, useful to users, it really needs to be a close proximity to the contracts. And that means a few different things. Number one, it needs to follow what the contract logic is actually doing. So a lot of times you might have a front end and you might see the smart contract function and you just assume, oh, it's going to do this. Or you read a parameter like, you have a value called delegator, and you might just assume in your head like, oh, the delegator field means this. But actually, it might mean something completely different within the context of that contract. And so it's very important that if you're building a front end, which is calling a smart contract, that it follows all of the procedures that those smart contracts are written for. And the tests and also reading the smart contract audits are a really good way to do that. I cannot tell you how many times, specifically on the Aave interface, that there has been a smart contract that has been attempted to be integrated, and you create a first implementation, but then you realize, wait, actually one of these parameters isn't what I thought it was, or if I pass a certain value to the contract, it can actually, do some special behavior, such as, passing a -1 value might represent the maximum value. And so it can save you a lot of development time and also headache debugging by just really making sure you understand the first principles of the contract first before you try to build out these transactions. And then also, whenever possible, querying data directly on chain. Especially lately, there's a lot of focus on sort of these infrastructure solutions to, simplify the process of querying contracts. But a lot of times what you'll find is that if you use sort of these libraries or you use these index services, you're introducing a lot of complexity, and also you're introducing a lot of risk into your application, because basically, those data providers are not guaranteed to return the results that you want. Whereas when you're querying a smart contract directly and you have a reliable RPC connection, you are guaranteed to get back the data, which is actually represented by your application. So for example, on the app.aave.com front end, all of the data which is fetched for, the markets or individual dashboard users, this is all queried directly on chain, which lets users know that, the balance that I'm seeing inside my front end is actually what's happening on the blockchain, and you sort of have that assurance. And really the second big practice to focus on is wallet considerations and wallet connections. So probably the biggest, anti-pattern when it comes to wallet connections is the application that requires you to connect a wallet before you're seeing data. Obviously, as a user, this is not what you want to see. And really, there's a pretty simple way to get over this, and it's separating the application RPC from the wallet RPC. So sort of what this means is that whenever a user connects a wallet to an application, that wallet actually has a blockchain connection inside of it. And so you can use that blockchain connection to query data for your application. And most of the time when you see these front ends which require you to connect a wallet, it's because they're relying on this wallet RPC in order to perform these queries. But this doesn't have to be the case. You are able to add other RPCs to your application, things like public RPCs, Alchemy, and Fiora, which are basically separate from the wallet and querying the blockchain state without having to rely on the wallet. So this is definitely a huge pattern to take note of. And also just in general about wallet connections, I'd really recommend to become familiar with a wide variety of wallet connection types. It's easy to sort of get attached to one specific library. Some of those common ones, Web3 Modal, Web3 Onboard, Web3 React is another big one. But sometimes it's actually really helpful to understand wallet connections at a low level. This is most helpful when you're trying to either debug something or script something really fast. So a lot of times you want to just create an application and you just want to send a transaction with MetaMask. You don't want to go through all this overhead of having to, create all of these different components. If you understand that basically you can create a front-end web page which is able to connect to MetaMask in about 10 lines of code if you just follow basically the documentation of Ethers or VM. This is a really powerful tool, and it can help you to really expand your skills as a front-end developer. And next is sort of the considerations when going multi-chain. So changing network within an application is a really common thing to do when you have a multi-chain application. So for example, on the Aave interface, you might click that market toggle button to switch between looking at Ethereum and looking at Avalanche or looking at Polygon. It's a really, really not a good pattern if every single time you want to look at different data in your application, you're telling the user, hey, you need to switch your wallet to be connected to this network as well. And basically the solution to this is the exact same solution as the previous slide, which is separate the application RPC from the wallet RPC. Your application should be able to switch networks on a fly to switch between Ethereum and Polygon and Arbitrum and Optimism without having to rely on the wallet to make that switch. And separating those RPCs is how you make that happen. And then sort of the second step to that is that once a user is actually trying to perform a transaction, that's when their wallet actually needs to be on that network. I should have put a screenshot in here, but on the Aave interface, the way that it looks like is that if you're trying to perform a transaction and your wallet is not connected to that network, it basically just blocks out the modal and it says, hey, you need to switch your wallet to this network. And you're able to do that in a single click using the ETH switch network RPC call. And then finally, the last thing here, this is sort of kind of an underdeveloped area at the moment, but Wallet Connect V2 actually introduces a lot of features which help with sort of this switching between different blockchains and switching between different methods with like smart contract wallets and EOAs. And they introduced this thing called the CAIP25 standard. And basically what this does is it creates a standard way for your dApp to send a message to the wallet to say, hey, I would like to request a connection. I need you to be able to connect to these specific networks, and I need you to be able to query these specific methods, like querying the chain ID or sending a transaction. And this is how you're able to basically get these guarantees inside of your application where it's like, if my wallet is connected and I am connected with this standard, then I know that my wallet is going to support these things. I don't think there's been too much development yet with how exactly this could make like the multi-chain user experience better, but it's definitely something to look into if you're interested in really bringing down the barriers to multi-chain wallets. And next, we're going to kind of talk about the architecture of an application. This is not so much related to user experience, but developer experience. So while you're kind of building these applications, a lot of times, you'll create a page layout, you'll import your wallet library, you'll query the contract data. So you're querying this data from the blockchain, but then everything after that is just complete spaghetti code. There is no logic or reasoning behind how things are put together. You're querying contracts inside of these massive components. And this is not exclusive to, lower level projects. If you look at any code base of a major, Web3 front end like Aave, like Uniswap, Compound, they're all going to sort of have this to a certain extent just because of the complexity of querying this data. And so it's really important to understand how we can avoid this and how we can actually make the code maintainable. And it's actually going to help the user experience a lot because you're able to build things much more efficiently. So what are actually the causes of this spaghetti code? probably the number one is vanilla JavaScript. We'll cover it in the next slide in more detail, but next is separation of concerns. So basically having your application trying to do too many things inside of one specific component or inside of one specific hook. And then the next is the death spiral of hooks, or this infinite re-rendering. So many applications that you go to, especially lower level ones, are just full of these React, use effect, use context, death spirals of re-rendering. And we'll show some patterns of how you can actually try to avoid that and make your app as fast as possible. So on the topic of vanilla JavaScript, TypeScript, if you are writing front-end applications, I truly believe that it is not optional. And I think there's three main reasons for this. Number one is that the blockchains themselves are using static typing. So every single time you call a blockchain function, a read method or a write method, those parameters that you are passing in and that you are receiving, they are strongly typed. And so the analogy that I like to give is that using vanilla JavaScript when querying blockchain interactions is the equivalent of having a 4K TV and then using component cables to plug into it. Why are you going to lose this resolution if you have it right in front of you, the most reliable type system that really exists in any database today? The second reason is that TypeScript is a superset of JavaScript. If you haven't used TypeScript before, JavaScript is TypeScript. You don't have to change any of your applications in order to get it to run, with one exception, which we'll get to in a second. The third is that if you ever just don't want to implement TypeScript, it's really not, I mean, it's an anti-pattern to use TypeScript ignore in a production application, but there's really no excuse not to use TypeScript, because if you don't feel like defining this 3-mile type, you just TypeScript ignore. And the last thing I'll mention here is that if you're going to be using TypeScript, turning on strict mode is essential. What strict mode does is it actually compiles the TypeScript and it'll throw a build error if one of your types doesn't line up. So if your function call is expecting that you're going to be passing a number or a string, and in reality that type is being passed as undefined, or maybe it's a variable type, it could be a number or a string. If you're using strict mode, this will actually throw an error inside of your build and say, hey, this type is not correct. If you're using TypeScript without strict mode, it just gives you a console warning. And let's be honest, nobody is checking their console warnings. You're only going to check these things once they error. So TypeScript is a must, and understanding basically that blockchains are statically typed, therefore using TypeScript on the front end is a really big jump. So how do you actually implement TypeScript in your applications? The Web3 libraries that are most common are actually make this super, super simple. So Ethers, Web3.js, and Truffle, which are kind of the most common libraries. Truffle, unfortunately, I would never use that. But TypeChain is a library. It's produced by Death Crypto. I don't know I don't have the link here, but it's inside of the resources. Basically, it's a library which you're able to add as a plugin to your Hardhat or your Foundry project, and it generates these files, these TypeScript files. And whenever you plug these files into your application, you actually get a type-safe SDK. So what that means is that, say I create a type chain mapping for the Aave pool contract. So whenever I have that type chain object inside of my code, now I can type pool dot, and it'll show all of the methods that are available. And if I want to call the pool.supply function, it'll tell me, hey, these are the parameters that you need to pass, and here is the types of each of these parameters. So when you have type chain and you combine it with TypeScript, it's almost impossible to actually run into a type error when you're calling these smart contract functions. And Veeam actually even takes it to the next level. And they actually support this type safety natively. They also have a lot of helpers when it comes to generating signatures. So I mentioned on the signature slide, you have this EIP 712, signed typed data. Typed data is really, really common when you're trying to work with signatures. And it's kind of a pain to work with, because if you're trying to get a user to sign a specific piece of data, if a single piece of that data that you're signing is not correct, say that your application is expecting the amount to be, a specific decimals, and you're not passing the correct decimals, or you're passing the wrong type, a number in place of a string. These are mistakes that are really common to make. And even if you're using type chain and TypeScript in these libraries, it's difficult to catch. But with Veeam, they actually provide these methods for you so that you're able to build these signatures and build this transaction data in a really, really efficient way. So currently the Aave interface, if you were wondering, does use Ether's V5. But I would strongly say that Veeam is probably the most advanced library today. And if I was to build a new application from scratch, that's definitely what I would try to work with, just because it has the latest and greatest features. So the next thing is separation of concerns. So if you think back to sort of the Web 2 diagram that I showed earlier, where you have this back end and you have this front end, you have these really clearly defined rules where your logic is completely separate from your view components. In Web 3, it's really easy to get away from this pattern, because when you're actually querying the blockchain and you're querying these indexing services or you're querying these APIs from your front end, it seems logical to just, I'll just put it in the same file where it's being displayed. But this really creates some hassle, especially when you're trying to maintain the code, because you'll just end up with these massive files, and it'll lead to actually the third point of this as well, where you're getting this death spiral of re-rendering. And really the practice which I would recommend most is treating your contract interactions and really any external service, whether you're calling a subgraph, your smart contracts, an API, or you're just formatting code. So whenever you get data back from the blockchain, as most of you probably know, it comes back in these weird formats, these integer formats which aren't formatted with decimals. And so a lot of times you're going to want to convert these into the correct decimals, and you're going to want to compute fields. So for example, on the Aave interface, we have this library called Aave Utilities. And basically what we've done with this is we've created these two separate packages, which says the SDK for reading and writing contracts. So when we're going to fetch data, or we're going to build that supply transaction or that borrow transaction, every single piece of code for those methods is actually not even stored inside of the front end. It's in this external package. And the Math Utils library is a completely separate package for formatting this data. And a lot of times this last part, computing fields on the UI, this is actually probably where the separation of concerns comes in the most. It's when, say, for example, you have a contract where you're querying an amount and a price, and then you want to do something with that information. You want to calculate, okay, based on these amounts and the prices, I want to show the user a certain piece of information, or I want to allow them to build a transaction like a borrow or a withdraw. And so a lot of times you're going to be doing these computations, but if you do these computations inside of your view components, you're going to be running them over and over and over again. And separating these concerns and only running this code once and having it in a totally separate place is a really great way to sort of get around that pattern. Next is asynchronous code. So when you're calling the blockchain, most of the time you're going to be calling multiple smart contracts at once. You're going to be calling multiple indexing services, especially if your application is doing something like querying multiple DeFi protocols at once. Say you're building a dashboard for Aave and Compound and Uniswap. All of these are going to be different specs of asynchronous code. And really just the number one tool in your toolbox should be React Query. React Query is not specific to React. It does work with Vue and Svelte as well. And it's really just a phenomenal library. It's a single dependency, so you're not really adding too much to your application. And what it allows for is it manages the multi-chain and multi-data source state with ease. So really the way React Query works is it's kind of a key value store where you're able to say, like, for example, say I want to have a store for all of my different Aave markets. I might have one key for the Ethereum market, one key for the Polygon market. And so whenever a user is switching that market from Ethereum to Polygon, React Query makes it super easy to, keep that data cached and then invalidate that data when it needs to be updated. And this is just so much better than trying to handle this all yourself. A lot of applications still just use, the vanilla fetch API with JavaScript, which works fine for some use cases, but it leaves so much on the table when it could be dynamically rendered. You could have pagination. You could make sure that specific contract calls are happening together. So say I want to have a dashboard where I'm updating all of my markets at the same time. With React Query, it's super easy to just invalidate all the markets at once and make sure that all of your data being fetched is fresh. So yeah, anytime you have asynchronous code, React Query is definitely something to reach for. And then next is testing. So testing is something that really goes overlooked within the front-end world. I think really React is kind of the main culprit of this because it is just so difficult to test React code, specifically hooks, just because React hooks, they can only be called from other hooks. So you can't call them conditionally, you can't loop through hooks. And so it makes it really difficult to write tests for React specifically. But if we go to the separation of concerns, if you have your contract interactions and formatting in a separate library, for example, the Aave contract helpers, the Aave math utilities, this is where it's actually super easy to write tests because there's no rendering actually happening here. All of the code inside of these packages is just static code, which is the easiest to test. And so, for example, in the Aave packages, actually, there's a threshold actually that new publishes to these packages are not allowed to be pushed unless there's 100% test coverage on every single line. And that's actually probably something that I would recommend. And because Jest, if you haven't used unit testing before, it's actually super easy to get started with, 5-10 minutes, you can understand how to actually create a test for something. And the other killer use case that I want to highlight here is artificial intelligence. So blockchains are statically typed. If you go to ChatGPT and you pass in a smart contract and you pass in your front end, you say, I'm receiving this data from my smart contract and I would like to use it to display these things on the front end, it can basically write the test for you because it has all of the context that it needs from the blockchain. It knows when you call this function, I'm going to be getting data back of these specific types. And so it's super easy to generate unit tests for it. And once you start using AI to write unit tests, you'll want to keep that 100% unit test coverage. And if you're ever struggling to figure out what to test, look at the contract tests. Most smart contract repos will have a very extensive test suite, obviously for auditing purposes. And you can really look at these and gain inspiration to see what should my front end actually be doing here. Next is the death spiral of hooks. This is kind of what all of these front end practices have been building to, which is avoiding these cascading re-renders. You'll notice this so much on especially, hackathon level front ends where, the user experience is severely degraded because every single time you go to do an action, you have this constant loading, especially when it comes to wallet connections and transactions. And the reason this happens is because a lot of your wallet state is happening inside of hooks. A lot of your data fetching is happening inside of hooks. And if you're not separating those concerns, a lot of times it's really easy to have just this massive shared context. So React has this thing called the context API, where you're able to generate providers. And a lot of times your application will just have this big tree of providers. And if you're not careful, what can happen is you have a provider that gets way too big, and it bogs down the entire application, where basically every single time that something is changed, every time a decimal changes on the front end, it's rerunning just this massive piece of code. And so the way to avoid this is using state management libraries. The two that I see most commonly, especially with Web3 things, are ZooStand and Redux. And so what these allow is you to have a modular global state. So if I have a blockchain connection and say I'm querying 5 different things, I'm querying token balances, I'm querying balances inside of Aave, balances inside of Compound. Now, what you can do with a modular state management is anytime you're using these things inside of your application, it'll only re-render when that specific thing changes instead of re-rendering the Aave data when the token balances change and vice versa. So it really just creates these simple patterns for re-rendering things. And then the last thing here is that the first thing that almost every developer reaches, also, I want to apologize. This presentation is mainly focused on React, but that's mostly because almost all of the major Web3 front ends are written in React. Almost 80 to 85% of the top 50 DeFi protocols use React in their front ends. And so even if you're not running your front end React, I still think it's important to understand these patterns. And React.memo and UseMemo are two really important tools to add to your toolbox. They sort of serve as a replacement in some places for UseState and UseEffect. So once you start using use memo, you'll find all of these different places where, oh, actually, maybe I should have been using this instead of use effect because I could have saved some re-rendering. And sort of once you use state management and you're memoizing your code, you'll pretty much never have to worry about re-rendering. And then the final development tip is fork testing. And this is probably maybe the most important thing of the entire presentation, is that the best way to test a front-end application is to test it on a live network. And what fork testing allows you to do is it takes the current state of a production or a test network, and you're able to simulate any function call. So I'm able to mock myself as any address. If I want to be vitalik.eth and see what my application would look like if I were using it from this specific address, you're able to do that. And the tools which are most useful for this, you can do it inside of smart contract libraries like Foundry, Hardhat, Ganache, but Tenderly is probably the biggest time saver that I've probably ever found within my Web3 career. It has so many features, which is going to save you so much time when it comes to debugging. So this is kind of what it looks like if you create a fork inside of Tenderly. I'm not a paid sponsor, by the way. I just really like the product. What it gives you is you create this fork network and it spits out an RPC. And so what you're able to do is you're able to take this RPC and you're able to add it to your wallet. And you're also able to take this RPC and you're able to plug it into your application. You're able to fund the accounts, send any amount of tokens to these accounts, and then you're able to do these simulations. So you can either do the simulations by, calling the smart contract methods through your RPC. So for example, like if you plug this RPC into an Aave interface and you wanted to query data, anytime that your front end is querying the RPC, it's going to show up as an entry inside of this table down here. And they also have this simulation tool where you're able to manually call them yourself. And it's such a powerful tool because there's so many cases where you have a case where, hey, I want to test this one specific token. Like, what does it look like if someone has 1 million of this one specific token? And when you have these really fine-tuned simulation tools, you're able to run a simulation and pass yourself these tokens and see exactly what your app would look like in those scenarios. And then once you actually generate a simulation, it's probably too small to see a lot of the details here, but Tenderly gives you so much information about a transaction, including the line-by-line stack trace. So if you're ever calling a smart contract and you're getting the dreaded gas estimation error, which can mean any one of 1 billion things, you can actually step through your code line by line and see, oh, this is the exact line that this code failed on, and here's the exact condition. Just a super powerful tool for debugging, especially if you're trying to integrate a smart contract. The thing I've found this most useful for is actually signatures. Signatures are notoriously hard to develop because they have to be type perfect. If they're not type perfect, you're going to get an invalid signature error. And when you're using a tool like Tenderly, it's super nice because when you generate these signatures and they're invalid, it'll tell you the reason that the signature is invalid. Maybe the deadline is expired or the nonce is too low. That'll save you so much time with debugging. So how do you actually integrate to fork testing? There's kind of like 2 main ways to do this that I've seen. The first one is to create a way to inject a custom RPC. So that RPC that I showed on the last screen, that's like your Tenderly RPC where you're able to perform these transactions. And if you create a way to sort of put this in your application, the way that we've implemented it at Aave is we do it through local storage. So you're able to paste in your browser console like local storage.setItem fork RPC, pass in the Tenderly one, and whenever the front-end interface sees that local storage variable, it says, oh, I want to enter fork mode, and it switches the UI to now use this fork RPC instead of the regular RPC. And then the second way to do this is actually using the wallet. I know I mentioned twice before that it's a really good idea to separate the app RPC from the wallet RPC, but for this specific instance, it's actually really efficient to just say, to have an option inside of your app to switch to the wallet RPC. For example, Uniswap actually does this by default. So by default, they're going to use the RPC in your wallet, but then they check that if the network is changing, then they're going to use the one inside of their app. So you can get really complicated with this stuff, but the point is you just need some way to test your front end with a fork network. This is the best way to make sure that all of your code is working properly. Next is security. Security best practices are something that I think a lot of front-end developers kind of overlook. They assume that a lot of these security concerns with blockchain are sort of handled for them on the smart contract side, and your front end is just sort of this dumb view layer. The wallet is going to handle all the authentication, the contracts are going to handle all the verification. My front end can just be this super simple thing. But in reality, it's actually really important to understand the security. Probably the most common mispractice that I've seen is storing secrets or API keys inside of environment variables. A lot of times people think that the .env file is just this completely sealed off, isolated thing, but that's actually not true. Whenever you build your front-end application and it's actually served onto the web, those API keys and those secrets are actually injected directly into your build. So if someone views the page source and you're storing something like a private key inside of your front end, that's something that is publicly visible, and it's really important to be mindful of those environment variables. Use best practices with access tokens. This isn't something that's super common with Web3 front ends, but specifically with the Lens protocol. The Lens API is sort of this full stack suite of sending transactions through their dispatcher, and they use these access tokens to sort of facilitate that. And I actually link a guide here at the end for best practices around that. Monitoring dependencies. A lot of times, a really common way that hacks sort of occur on front ends is that hackers will look at the dependencies that a project is using. They'll see oh, you're using this specific version of the package, and then they'll go to that package and see, well, since that version, say they're using 0.1, in version 0.2, they actually patched out this really critical security vulnerability. And so they know that any application which is running 0.1 is now vulnerable to this type of attack. This is why it's really important to turn on Dependabot. Make sure that you're monitoring these dependencies and updating them as you're needed for these security updates. And then lastly, checking how you're actually deploying your application. So a lot of times, this actually isn't a concern for hackathon level projects, because most of the time you're probably just going to reach for something like Vercel or Netlify, which is kind of handling all of this for you. But for a lot of the open source front-end applications like Aave or like Uniswap, the deployments are actually happening inside of GitHub Actions. So they're writing these scripts to basically upload these every single time that a new build is generated. It uploads it to IPFS, it uploads it to IPNS. And you got to make sure that those access tokens are secure, because if you lose your token, you lose access to your website. There's the doc I mentioned about the key management. And then kind of just some bonus rapid fire tips that I really couldn't fit into a cohesive slide is never use production wallets when testing things. And in order to actually just completely make this not even a possibility, a great practice to do is inside of your web browsers, there's actually a way to create multiple profiles. And so what you can do is you can create one profile which has maybe your MetaMask wallet, which actually has real funds in it, and then you just have this totally separate browser profile that's only used for testing. And this just makes sure that you can't lose funds. It's really unfortunate if you were to, send funds to a piece of code which is in progress and you accidentally call the smart contract function you didn't want to call. This just avoids that altogether. Windows, it's the most common development environment actually for blockchain developers, surprisingly. If you're using Windows, like I am, use the Windows subsystem for Linux. It will save you so much headache when it comes to debugging packages. There's just a lot of libraries, specifically with Hardhat and Foundry, that just do not work with Windows, but they work fantastic on the Windows. So WSL stands for Windows Subsystem Linux. So every modern Windows machine basically has Linux built into it. So take advantage of that and use it. And then also another tip is that a lot of people use IPFS for uploading their front ends and making them immutable. But if you're just using IPFS, a lot of times it doesn't really provide the immutability that you want. Because say you're merging changes into your front end, and every single week, you have maybe 3 to 5 different versions of your front end going out. Every single new version is a new IPFS hash. And so as an end user, what's the difference between a malicious IPFS hash and just one that is published routinely? And IPNS allows you to create a static link. So for example, for Aave, we use the IPNS name app.aave.com. So if you query the IPNS name app.aave.com, it'll return the latest IPFS hash for your front end. And this is just a way for people to, verify that the source code they're interacting with is legitimate. And also it provides alternative gateways. So say the app.aave.com DNS is down, you now have this alternative where you're able to use this IPNS name and say, hey, I know actually the IPFS hash, which app.aave.com should point to. And so I can use any different IPFS gateway to access that. It's just a way to provide that decentralization, that immutability to your app. And then finally, be mindful of base assets versus ERC20. There's a lot of caveats to using ETH or using Matic or any of these different base assets as opposed to ERC20. And it's important to keep those in mind. So yeah, that's basically all I have. That was kind of a rapid fire thing, but thank you guys so much for listening. And we actually do have about 10 minutes. So does anybody have any questions? Yeah.
You talk about the can you talk about this type of login that use, for example, your email and connect this email with a wallet? I'm not sure how it's working. I mean, with the secret phrase, or what happened with the keys, or if this connection is as SQL or what kind of database?
I'm not sure I fully understood it, but you're talking about like logging basically like the wallet keys?
No. There are a login, but using your email, for example, Google, typical login in Web2, but these have connection with a wallet, but you don't know your key of your wallet, and
yeah,
I imagine
that's actually something that's really become popular lately, is using sort of those Web2 logins to sort of represent a wallet. And there's kind of two different approaches to it. One of them is this idea of a scratch wallet, where basically I pass in as a user an email and a password, and it'll just generate me this brand new wallet. I think this is basically what Frontend was using, this new application that launched. And it really creates a good user experience because now users that don't have a Web3 wallet can access your application. But there are obviously a lot of security concerns around that. You have to make sure that whatever service you're using to create that wallet doesn't have access to those keys or has a way to export those keys. So there's a lot of security considerations around that, but it's definitely something that is a huge like user experience boost. I'm not sure if that answered the question or not, but yeah. Got a guy in the back.
Yeah, hi. But the question is how you manage the security in your project regarding the changes of the code that can produce front-end hacks. Like, for example, a developer changing the approval address instead of the Aave contract to some rogue contracts that is going to steal the funds. So how you manage that, how that slows down your process of releasing new versions and all that stuff.
Yeah, that is extremely important. Basically, the way that it's managed in most applications is through GitHub fine-tuned access controls. So basically, inside of your individual GitHub project, you can specify, I need X number of Y people in order to sign off on this release. The other really, really important thing around that is inside of your GitHub organization where you're allowing people to approve and merge these pull requests, you're actually in GitHub able to mandate that they have two-factor authentication enabled. This is a really, really important thing to have turned on. There have been multiple instances in the past where basically Web3 front ends were doing all of their deployments through GitHub, and then somebody's GitHub account got phished, and then they're able to, overwrite that deployment and, approve to a different address. So setting very strict approval requirements, requiring 2 or 3 approvals out of a very small subset of users. That's one thing. You don't want to have, 10 different people which are able to approve the pull requests, which, is kind of goes against the pattern of, having sort of this like decentralization, but at the same time, you can sort of create these like structures where you have like, one GitHub account, which might be shared by 3 people. And, it has, very specific access for controls where it's able to update, the signers of the repo. Because basically in any given repo, no matter what you currently have set up, there's always going to be an admin which is able to change those things. And so it's very important that not only do you have the proper number of reviewers set up, but also that there's a very select few number of admins that have the ability to change those things. So yeah, that's a really important consideration.
Hi, really good talk, by the way.
Well, thank you.
I had a question about multi-chain. I know that Wallet Connect V2 is pretty cool into what it's doing, into handling multi-chain beyond the fly. But right now we have like a bunch of wallet providers like MetaMask that actually require you to still refresh your browser if you want to change your chain. Then you got Rabbit, which doesn't, Frame doesn't, and then there are like thousands MetaMask copies that actually enforce you to refresh your browser. How can you better handle the UX for any kind of user into when they want to do a specific action, they need to change their network into their wallet into that network? How can we try to avoid refreshes apart from going into more EAPs, into getting better like standards from our wallet providers? How can we, from our position as front-end developers, improve that experience?
Yeah, that's a great question. I would say there's like 2 sides to it. One is sort of like there's a lot that really you can't control as a developer. I can't control what MetaMask implements or what Frame implements. So you're kind of bounded by what they enable. But on the flip side, you are actually able to do these really creative things, specifically with EIP 4337 and account abstraction, where you're basically able to create this smart contract wallet, which might work on multiple chains. And so like you might have the wallet is only connected to one chain, but based on the way you abstract it, it can actually represent transactions on multiple chains. So that's probably the best way to do it. But really the big solution and how you actually solve those UX concerns is you talk to MetaMask, you talk to Frame, and try to get them to actually adopt these EIPs that don't make you switch your wallet every single time for the network, because it's such an annoying pattern.
Bueno, chicos, en realidad el tiempo nos gana, mil disculpas. Tenemos otra charla muy buena también sobre Starnet. Entonces, un aplauso. Mil gracias, Andrew.